Hello, today we're going to talk about nullity and rank of linear mapping. So let's start the topic. So what we have, so if we have a two vector space V and W, so we have a vector space V and W and they are vector space over the field of a real number, so they are real vector space. So V and W are two vector space to real vector space. Basically we also can work with complex vector space, but when always takes V and W are either two reals or either two complex. Don't take one real, another is complex. So V and W are two real vector space, and if we have a linear mapping, so if we have a linear mapping V from W, so we already find out that the what is called the kernel of T. So kernel, we already seen that kernel of T is a subspace, so is a subspace of V. We already have find out. If you have not seen that, please check out my previous video. So we have find out that kernel of T is a subspace of V, and the image of the linear mapping image Im of T is again a subspace, so it's a subspace of the vector space W. So kernel of T is a subspace of V and image of T is a subspace of W. Because they are subspace, we can think about the dimension of that subspace. So here we are going to define, so kernel of subspace, the kernel of T also called the null space. Okay, so kernel of T also called the null space. So kernel of T is also called the null space, also calls the null space. So because kernel of T is called a null space, what we're going to do, we're going to define the dimension of kernel of T. So dimension, because this is a subspace, we can talk about dimension. So dimension of kernel of T will be called the nullity of the linear transformation T. So this is called the nullity of the linear transformation T. Similarly, the dimension, they are all definitions. The dimension of image of the linear transformation will be called the rank of the linear transformation, the rank of the linear transformation T. So in this topic, the nullity and rank, we have a beautiful theorems also called the Sylvester law, and the theorems is called, so let me erase this first. So remember that what we have till now, we have a linear transformation T from a vector space V to another vector space W. So W may be equals to V and may not be equals to V. So we have a linear transformation from V to W. Then kernel of T is a subspace of V. We have already seen that, and dimension of kernel of T is called the nullity of T, and the image of the linear transformation is also a subspace of the vector space W, and the dimension of the subspace is called the rank of the linear transformation T. So here we have a theorem. We're going to use the theorem later. So first let me erase this part first. So here we go. So here we have a theorem. This is called the rank-nullity theorem. So rank-nullity theorem also calls the Sylvester law. Rank. So rank-nullity theorem. So what is called, so it says that if V be a finite dimension vector space, finite dimensional vector space, so if V is a finite dimensional, so dimension of the V is finite dimensional vector space, and we have a linear transformation, so and T from V to W be a linear transformation. So if we have a linear transformations or a linear mapping, so they are the same thing. So V is finite dimensional vector space, and we have a linear mapping T from the vector space V to the vector space W. Then it says that the theorem says that, we don't have the proof of the theorem, it says that nullity of T plus rank of T, that's why rank of T is equals to dimension of the vector space V. So that's why it is called the rank nullity theorem. So nullity of T means what we have to do, we have to find the dimension of kernel of T, and rank of T means we have to find the dimension of image of the vector space, image of the linear transformation T, and dimension of image of T. If we add that 2, we get the dimension of the vector space V. That's why, because we write in this way, so that's why finite dimension is very important, otherwise it has no meaning. So let's verify the rank nullity theorem. So let's see an example. So here we have the problem. So we already do this problem previously, but let me do it again. So it says that question is verify the rank nullity theorem for the linear mapping from the vector space R3. So V is over here, V is over here is R3, and we know that dimension of R3 is 3, so it's finite. So T from R3 to R3 is linear transformations, and defined by for any vector x, y, z goes to the vectors which has a first coordinates x plus y, second components y plus z, and third components z plus x. So in this way the mapping is defined and is a linear mapping. What we have to do, we have to find the dimension of kernel of T and also find the dimension of image of T. Then we have to verify the rank nullity theorem. So let's do it. So first let me erase this first. So here we go, just let me erase this first, then we're going to write what is the definition of linear transformation. So definition of linear transformation is, so T is a mapping from the vector space R3 to the vector space R3, and it's defined as, is take any vector. So here vector is the triplet x, y, z. It takes the vector triplet to the vector x plus y, y plus z, and z plus x. It's true for all x, y, z, and this is a vector of R3. So what we're going to do, we're going to first find the kernel of T. So we have already find that out in our previous video, but let me repeat that first. But quick, I will do it quickly, very quickly. So x, y, z belongs to R3 such that T of x, y, z have to be equals to the 0 vectors of here. So 0 vector of R3 is 0, 0, 0. So here we go. So if we have any elements, so if let we are taking any arbitrary a, b, c belongs to kernel of T, then what we know, so it satisfies the property over here. So because a, b, c belongs to the set, so it satisfies the property of the set. So that means T of a, b, c have to be equals to 0, 0, 0. Now look at the definitions. In these definitions, x is a, in the above definition b is y and c is z. So what are we going to do? So here we have a x plus y, so x is here a, y is b, so we get a plus b, and next b plus c, next will be b plus c, and it will be c plus a, and it have to be equals to 0, 0, 0. Now we have two vectors, they are equal, so that means each components of the vector have to be equal. So that means here a plus b have to be equals to 0, b plus c also have to be equals to 0, and c plus a also have to be equals to 0. So we have three equations, 1, 2 and 3. If you solve these three equations, you will clearly get the only solution will be a equals to b equals to c equals to 0. So kernel of T is contain only the 0 vector 0, 0, 0. So because it's contain only the 0 vectors, so that means kernel of T span by there is no another non-zero vector span the kernel of T, which means dimension of kernel of T is basically 0. Why? Because we have 0 vector, not non-zero vector. If we have one non-zero vector, the dimension will be 1, but here we have a 0 vector, so dimension of kernel of T is 0. So next going to solve, so always remember here if we have some non-zero vector, dimension will be the 1, but here we have only 0 vectors and it span only by the 0 vectors. So but we do not consider as dimensions. When we are talking about dimension, we are talking about the non-zero vectors, the vectors present in the basis sets, and we are talking about the non-zero vectors. So here we have 0 vectors, so dimension of kernel of T will be 0. So next see what is the dimension of image of T. So let's do it. So here we get dimension of kernel of T is 0. So let me write down somewhere at first. So next we are going to find the image. So here we go. So first let me erase this first. So what we have find out? So we have find out that dimension, sorry for my handwriting. So here we go. So dimension of kernel of T, or the nullity dimension of kernel of T is 0. So now what we are going to find? We are going to find image of T. So image of T, let me repeat that, is collection of all vectors x, y, z, because it's taking here any vector is of the form x, y, z. So it's a collection of all such vectors, and we already know that if we have the basis vectors alpha 1, alpha 2, alpha 3 of the vector space V, then T of alpha 1, T of alpha 2, T of alpha k in this way will be span image of T. So here the basis vectors of R3 are, so 1, 0, 0, 0, 1, 0 and 0, 0, 1. The three vectors are the basis vector of R3, which means we have already done this, but let me repeat this as fast as possible. So image of T obviously span by the image of the basis vector, so span by the vectors T of 1 0 0, t of 0 1 0, and t of 0 0 1. Okay, so now what's the value of t of 1 0 0? Put over here. So first find that out. T of 1 0 0. So if I look at this formula, so here x is 1, y is 0, and z is 0. So here x is 1, y is 0, so it gives me 1 plus 0, 0 plus 0, and 0 plus 1. So we get 1 0 1. So next, find that out what's the value of t of 0 1 0. So here x is 0. If I look at this formula, here x is 0, y is 1, and z is 0. So use that value, put over here. What we get? So we get 0 plus, so let me change the ink. So it gives 0 plus 1, 1 plus 0, and 0 plus 0. So we get 1 1 0. And from the last, again use the formula over here. So here x is 0, y is 0, and z is 1. So we get basically 0 plus 0, 0 plus 1, and 1 plus 0. So 0 1 1. So what we get? So is the span, the image of t is spanned by the vectors. So 1 0 1, 1 1 0, and 0 1 1. Okay, so let me do it. So it's spanned by these three vectors. Now if these three vectors are linearly, now we have to check is these three vectors are linearly independent or not. So what we're going to do, we find the determinant 1 0 1, the first row of the determinant from the first vector. So second row of the determinant from the second vectors, and the third row of the determinant from the third vector. So what we get? 1 minus 0 plus 1. So we get 1 minus 0 again. So we get 2, which is non-zero. Because the determinant is non-zero, so three vectors are linearly independent. So let me erase this first and write that down. So these three vectors are linearly independent. So the vectors 1 0 1, 1 1 0, and 0 1 1 are linearly independent. So linearly independent. So because three vectors are linearly independent and span image of t, so 1 0 so 1 0 1, 1 1 0, and 0 1 1 is a basis of image of t. Why this is a basis? Because this span, so to be a basis it have to span the vector space. So it span the vector space image of t, and also the three vectors are linearly independent. So span and linearly independent, so is a basis of image of t. So because now we have three vectors in the basis set, so the dimension of image of t is 3. So let me erase this first. So dimension, so what we get, so because we have three vectors, so in image of t, in the basis of image of t, so dimension of the vector space image of t is 3. So let me write that down. So dimension of image of t, which means the rank of the linear transformation t, is 3. Now if we add these two, So what we get? Dimension of kernel of T plus dimension of image of T is equals to 0 plus 3 is 3. Obviously this is same as dimension of the vector space R3. So here V is R3. So clearly the rank nullity theorem is verified. So verified. So it's clear. So this linear transformation, the given linear transformations satisfy the rank nullity theorem. So thank you for watching. Bye.